Yeah.
Okay, thank you so much for the organizers for asking me to give a talk. So I think I'm an outlier here in terms of my areas of interest, but probably and hopefully not in terms of my connections with statistical physics. So in this talk, I'm going to tell you a little bit about some interplay between privacy, which is growing to be a very important problem, and statistical physics. And in particular, we'll look at the problem of low rank matrix approximation. So, so my background is theoretical computer science. I'm not sure these slides are made taking into account the, the general aesthetics and style of talks in statistical physics. I've tried my best, but feel free to interrupt if something is not clear. I want this to be a useful talk for everybody. Thank you. Okay, so what I'm going to do is give you two vignettes of connections between privacy and statistical physics. One would be, I mean, both will arise from looking at a problem in low rank matrix approximation. Both are about adding some kind of a noise or sampling from some processes. In one case, we will see that looking at a particular problem will lead to an efficient algorithm to sample from the so-called Harishchandra, Edzik, and Zuber densities, which are well-studied objects in statistical physics. And in the other case, we will use ideas from the so-called Dyson Brownian motion to analyze these private algorithms. So that's these are the two pictures indicating the two topics that I will talk about. So let's start with the problem setup. So we are given a matrix whose rows consist, let's say, of users, and the columns consist of useful or important information about those users, which are also called features. You don't have to worry so much about it right now. You can just think of it as a matrix, which is an M cross D matrix, where M is the number of users and D is the dimension in which their features are. Something that will be important for this data matrix is what is called its covariance matrix, which is just taking the transpose of this matrix and multiplying it with itself. So this becomes a D cross D matrix. So think of D as small and M as large. You're also given a parameter K, and the overall overarching goal of this low rank matrix approximation area is to approximate this huge matrix, or rather its covariance matrix, by smaller dimensional matrix. So this is not a well-defined thing. What does it mean to approximate and so on? So let me make it a little bit more mathematically precise. There are two variants of this problem which arise in various applications. The first one is called the rank K covariance matrix approximation problem, where the goal is to compute a rank K matrix that minimizes a given distance to this matrix M. So this distance could be in terms of the Frobenius norm or the inner product, matrix inner product, and we will talk about it. The other is the so-called subspace recovery problem, where we just want to project this matrix into, or approximate this matrix by rank K projection matrix. Okay, so and the simplest example of this is computing the principal eigenvector of this matrix and looking at the rank 1 matrix formed by the principal eigenvector. So this is also something that people refer to as PCA, and probably many other names in this. The important point here, as far as I'm concerned, is that there are efficient algorithms to solve these problems, and in fact that's why they are used so often. To solve the subspace recovery problem, I have to compute the eigenvectors of this matrix M, and then build the projection matrix from that. By efficient, I mean polynomial time. And these problems are ubiquitous in a lot of different areas of computer science and mathematics and statistics. I'm guessing, yes. Yeah.
You have some questions in mind to answer that go beyond that, right? So maybe can you say a little bit more?
I'm sorry, I didn't get the question.
No, so if the subspace recovery problem, I mean, is a problem which, as you just stated, has a well-defined solution.
Yeah, it has a solution. So you look at this matrix M, and you compute its eigenvectors, and you compute its eigenvalues. Then let's say you order the eigenvalues in the decreasing order of magnitude. And well, these are all, I mean, I didn't specify it, but this is a positive semi-definite matrix. So all eigenvalues are real. So you can order them. And then you just pick out the top k eigenvectors. And then you form this projection matrix, VK transpose. And you just output that. That's in some sense your approximation of the data matrix, which has essentially all the information depending on the choice of k. So that's why it's used so much in practice, because this D cross D matrix often is very large, and you can't really work with it when it comes to doing pattern mining. So a small, I mean, so what people are looking at in many disciplines is a small kind of signature matrix, which has essentially all the information that you need, and yet it's small to represent, it's small to do computations. That is the reason why we kind of do this. No, this comes from the domain, unfortunately. So I mean, the people who have this, who work with data, they will have some idea of what the choice of k would be, right. But it will not be very large, I guess. Right. If it is very large, then we don't need to do all that stuff.
Yeah. So to find this VKs, first you have to actually diagonalize the whole matrix, and right.
That's right.
But that itself is a big problem, I guess, right?
That is, yeah, but that still has a, I mean, that's right. That's something you have to do.
Okay.
Yes. But that's, I mean, so when I say efficiently computable, I mean in terms of polynomial time versus not polynomial time. Yeah. Great. What is polynomial time? Yeah. Okay. Yeah. I mean, well, if you start getting really precise, then we have to talk about approximations to these eigenvectors and eigenvalues, because these can be irrational numbers which you can't really represent. So in all of what I say, it is enough to compute good enough approximations to these things, as long as the running time quantifiably depends on the quality of the approximation. Okay. So that's, yeah, I'm not going into defining the models of computation here, otherwise we will not make any progress in this talk. But thanks for asking all these questions. These are great. So this is a traditional problem. There's nothing new here. What is new in the last few years has been the explosion of this, the explosion of personal data, which is being, on which these algorithms are being applied. So data, and this data can be very sensitive, and you would not want this data to be to come out. So what used to happen traditionally was that, a company has a data matrix of users. It wants to do some analytics on this, so it will give this matrix to this analytics company and say, here, can you do this computation for me? Now, if there's any breach or any such thing that happens, then you basically are releasing private information of all these users. So you don't want to do all that stuff. I mean, there are big cases of this stuff that happens. And I think one of them was this famous Netflix problem. I don't know if anybody here heard of the Netflix problem. Did you hear about it? Yeah, so Netflix at some point offered $1 million prize to anybody who could improve their recommendations. This is many years ago. The recommendations are still as bad as they used to be. As I think I'm spending more time browsing Netflix than watching Netflix. So, but nevertheless, jokes apart, I think they did release the so-called anonymized data sets where they did not mention the names of the users and so on. But people could very quickly deduce information about specific individuals. Okay, so this is something that happened. And in a small, by just looking at a small number of small size data sets, you could already start figuring out whether particular people are in the data set or not. So despite Netflix thinking that, oh, I've removed the names and some basic information, there's no way privacy can be breached. It's not the case. And I guess, I mean, if you never thought about this, I mean, basically this is the reason that even small, I mean, moderately dimensional data about people tends to be very unique. And I mean, if Yale releases salary information along with ethnicity and gender and so on, so you can imagine that with a very small number of identifiers, people might start becoming unique. Let's say if the gender is woman, the ethnicity is black. I mean, how many departments at Yale would have such a person? So if there is a department, then you single out a person whose information this is. So it's all very complicated. I mean, it's figuring out who the person is actually can be figured out. I mean, it's not it's not what I do, but I can imagine people figuring this stuff out very quickly. So anonymization is not that good an idea, and so you might think that, okay, how about releasing just the covariance matrix? I mean, at the end, the covariance matrix doesn't really have the individual features, right? Because I have taken the feature matrix and multiplied with its transpose and then output it. In at least many interesting applications, you can figure out you can from this information, from these correlations, also figure out individuals presence or absence in the data set. And that can have significant consequences, at least in the kind of countries like US, where insurance companies, if unchecked, can charge you premiums based on your medical conditions. There is a huge amount of stake riding on data and its release. Well, why do we want to release the data set? Because these are scientific studies. At the end, we want to do open science in some sense, right? We want to share data sets. We want others to be able to verify what we are doing. But then if the consequence of that is that individuals' privacy is compromised and they can suffer potentially life-threatening consequences, then we have to think harder. So this was a very short prelude to a whole area of privacy in computer science. And the key question is, how do we compute whatever we wanted to compute, which I talked about in the first slide, this low rank matrix approximation to a given covariance matrix in a manner which is private, useful, and it's efficient. So all of these words are put in quotes because I haven't even talked about what it means to do things privately. Usefulness, at least you get some sense of, because well, one thing I can always do is I can ignore the input matrix and just output a random matrix and just give you that. That's fully private, right? I mean, there's no correlation between the input and the output. But that's not very useful. Okay? So that's not a good idea either. So there is a tension between usefulness and privacy. And at the end, efficiency sits on top and say, okay, you might be able to give a algorithm which in principle is both private and useful, but may not have an efficient algorithm. You might not, it may be like a needle in a haystack. Yes, the needle is there, the haystack is huge, and I'm not able to find the solution efficiently. So, any questions? Okay, so I'll demystify things slowly. Let me talk first about privacy. So this is in no means a settled thing, but there is this notion of differential privacy. How many people here have heard of differential privacy? No? Okay, so this is surprising to me because this is now being used in all your iPhones and Androids and everything. And in fact, one of the big successes was that Apple CEO coming a few years ago and saying that now you can feel safe about the usage of your Apple phones or Android phones or whatever, because we are using this methodology. So this was something that was, this is a definition. Differential privacy is a notion. It's not an algorithm. And the idea is to come up with a definition of privacy which protects individual users in the following sense, okay? In the sense that the outcome should not change much. The outcome of the algorithm should not change much whether an individual person participated or did not participate in a study or the input. Okay, so going back to the low rank matrix approximation case, if I took one row from the data matrix and flipped it with somebody else's information, the output should not perturb a lot. At least that's the essence of this idea. And one can argue that this is, first of all, so this is something that we will formalize and develop algorithms for doing this. It seems to be useful, and also you can prove many theorems about this these definitions, that once you get the output of a differentially private algorithm, no matter what you do with that output, you can never undo the differential privacy guarantee. There are lots of nice properties about these definitions. Yes. Yes, deleting. Yeah, so you can delete it or you can replace it by another individual. It's the same. Yeah, okay, good question. So what does a randomized sanitizer mean? So, unfortunately, privacy you cannot obtain by any deterministic algorithm. So I didn't mention that. I should have. If you have a deterministic algorithm, a deterministic algorithm is something which always does something identical, no matter. So once the input is fixed, the output of the algorithm is fixed. Okay, that's a deterministic algorithm. Such algorithms cannot achieve any kind of privacy. So that's right. You have to use a randomized algorithm, which has to be able to, which has to. So we will see, yeah, some examples of mechanisms. Yeah. Okay, so this is the definition. It's actually useful to look at it. We say that we say that a mechanism, this mathcal A, is differentially private if for any two neighboring data matrices, A1 and A2 in this case, the distribution of this mechanism is close to the distribution of the mechanism output on A2. Okay, and there are these parameters delta and epsilon. If you let delta to be 0 for a moment, then what it says is that, and if you think of e to the epsilon as 1 plus epsilon, then what this is saying is that at every point in the support, the probabilities have to be within 1 plus epsilon and 1 minus epsilon of each other, roughly speaking. So multiplicatively, the two distributions have to be close to each other. That's what this delta equal to 0 definition is. It's a more strict definition of privacy. It has stronger consequences. A slightly weaker definition is when you have this additional violation in terms of probabilities, and which is also very useful. It's epsilon delta privacy. Yeah.
So maximal of A is a matrix or
Well, yeah, in this particular case, it'll be a matrix because we are outputting a low rank matrix. But this is a very general definition. This could be any two input data sets, which, and you're supposed to compute some function of it. And all you're saying, because the distribution is, because the output of this algorithm is randomized, so what you want is that for any two neighboring points, the distributions have to be close. And I think now for people here, they might start thinking of connections to physics because, at the end of the day, this is a property which you can think of also as stability of a system. And what we are saying is we don't want to design any algorithm. We want to design algorithms which have some stability properties. I'm not told you yet. Yeah. So here is once again the problem, and as promised, now I'm making the notions of utility or usefulness more precise, and even generalizing this notion of low rank matrix approximation. So we are given this matrix M, which is the same as what we were given before. This is its spectral decomposition. And we are given some target matrix, a diagonal matrix lambda 1 to lambda d. And what we would like to optimize is the distance between the true best approximation, which is this, versus what we are outputting. So V hat is what we will output. And what we would like is that what we output is close to what we should have outputted in the Frobenius norm. It doesn't really matter for this talk whether I use Frobenius norm or this. This is just a matrix inner product. So this is just a trace of this times this. Yeah, lambda is something that is given to you as an input. So let's look at a more concrete example of it. So the subspace recovery problem, in there, the first k lambdas are 1 and the rest are 0. So this just gives you more flexibility to encode different types of low rank approximation. And if the first k lambdas are set to the first k eigenvalues of M, then this is the covariance matrix estimation problem. So these are some examples. And in the subspace recovery problem, I mean, if you look at this expression, this term is fixed. So this is not really part of the minimization. So what you really want to solve is this problem, to find the argmax over the set of all rank K projection matrices of the inner product between M and X. Okay. Very soon we will see the connection to statistical physics, just actually in the next slide. So if you want to ignore everything until now, you're welcome to do that and just focus from now on. Yeah, so the inner product definition between two matrices. This is the Frobenius inner product. This is just defined to be the trace of this. It's, if you view matrices as vectors, then this is the inner product in that space. Okay. Any more? Yeah. It should be. I think that's why I put the transpose. Yeah, these are square matrices. Yes. Yeah, these are square matrices. No, they don't. Star means conjugate transpose. Yeah, I mean, I think it's fine. But okay, if it is confusing all this notation, I think what I'm really saying is the following actually. So if you have, let's say, A11, A12, A21, A22, the inner product that I would like for this is the sum over I1, 2 of the inner product between Aij and Bij. And these are just two numbers, complex numbers potentially. So just the standard product of, okay, maybe. Yeah. Okay, so here is the beginning of the connection to some problems in statistical physics. So one of the ways in which you can achieve differential privacy when you want to do optimization is to essentially move the objective function to the exponent. So this starts looking like this Gibbs density. And here is a theorem which is not very difficult to prove. Actually, it's a few lines, which says that if you want a differentially private mechanism to maximize this quantity here, MXF, the inner product of M and X, then it is sufficient to sample from this density, which is the exponential of the inner product. You can, for practical purposes, set this epsilon to be some fixed constant, so you can ignore that. That's like setting the temperature in some sense. So the smaller the epsilon, the more spread out the density. So that's the high temperature regime, right? And the bigger the epsilon, it kind of, so what it's saying is actually something that probably in statistical physics people have been doing for 100 years, is instead of optimizing, you should be sampling. That's actually a way in which you can achieve privacy. So the question is, why are we optimizing today and not sampling? Somebody said something here. We don't have efficient algorithms to sample from this. And in fact, you would see that most of the machine learning has actually moved to optimization instead of sampling. Right? Yeah, so the question is, how do we sample from this density? So this result, well, this is an old result, 10-year-old result. So let me show you a little bit of the connection. Since I only have not so much time left. So one of the basic observations, which I think everybody here can see, is that this entity over which we are optimizing, this set P sub k, is actually not a convex set, but it is also not a nasty non-convex set. It's an orbit of this matrix lambda under the conjugation by unitaries. If you can just start with this diagonal matrix, which has k ones and rest zeros, and you conjugate it by unitaries, you can recover the entire set of all projection matrices. Okay, so that's one. So this gives rise to this notion of unitary orbits, which have been well-studied objects, and where instead of looking at this specific case, you can look at a general lambda. These are not just arbitrary manifolds; they have nice measures on top of it, so you can do probability on them. And the question that we are really asking is, can we sample from such densities? So these are exponential densities over these orbits. Okay. And this turns out to be related to a different looking problem, which was studied by Harish Chandra, Idrikson, and Zuber. Well, I guess Harish Chandra was the first person to look at it. And they were looking at densities of this form, where e to the trace of yu lambda yu star. I don't know, anybody here seen this stuff? Okay. So yeah, so this is something that I guess people here have seen. And well, it's not difficult at all actually to see that this density here is a density over an orbit by just fixing one of the matrices. So the problem of sampling from this HCIZ density is equivalent to sampling from this orbit. So while there were lots of proofs of writing the partition, computing the partition function of this, it was not known how to actually sample from this density efficiently. And when I say sample efficiently, I mean that running time should be polynomial in the input parameters. So that is the first result that was published last year, that we give a polynomial time algorithm basically to sample from these densities. So it has many applications in, like, of course, the problem that I mentioned of differentially private low rank approximation in the pure setting and the delta equal to 0 setting. Just the basic problem of sampling at CIZ density. Some of my physicist friends tell me that this is useful. I don't know. And then in statistics, there are all these densities called Langevin distributions and so on, which again, people did not know how to sample from. And given their form, they can also be viewed as certain entropy maximizing density functions. And so there was some earlier paper of mine where we were looking at this, and that's where the question of efficient computation was used. That's right. That's right. Yes. Yes, but so very, very good question actually, and thanks for pointing that out. So what we do is, even though the matrix initially is real, we can treat them as complex matrices. So the output of these algorithms will be complex. Okay, but what you can do is you can post-process these matrices and make them real again. And this is the power of the definition of differential privacy, which I mentioned, that no matter what you do after you have computed, it is not going to destroy the property of privacy. Yeah. I'm in touch with Zubair, so I mean, I mean, I'm looking forward to talking to him as well. Yeah. So, yeah. So this is, at least to the best of my knowledge, there is no proof before this of this work. Okay, so let me spend the next few minutes on the second thing, which is probably interesting to some of you, and I know Satya here has worked on that as well. This Dyson Brownian motion. So there is another way to do privacy if you are willing to relax this pure privacy, and that's actually computationally very simple. So now what you do is you add Gaussian noise to the matrix, to the input matrix, and then compute the low rank approximation. So here is the picture. So this was your original matrix M. So you add some noise to it, and then, and this is the manifold, let's say, of all rank K projection matrices. And let's say this is the matrix that you output. And this was, let's say, the best rank K approximation to M. You added some Gaussian noise here, and then you computed the low rank approximation of this new matrix. So computationally, this is easier. The question is, how far can these two things go? What is the, I mean, what's the, because there is a very non-linear step in this process, which is a low rank approximation step. It is not straightforward to approximate what the distance between H and H hat will be. So that's what we are doing here. And here, the key idea, which again is something trivial to start with, but was not done in the privacy literature. And I think this is where ideas from statistical physics can be actually useful in the design of such algorithms, is that one can view adding this Gaussian noise as Brownian motion. Well, so okay, so what? Well, but then there is this whole beautiful stuff by Freeman Dyson, which tells you how the eigenvalues of such matrices evolve and how the eigenvectors of such matrices evolve. And you can use, and we do use the stochastic differential equation to track the change in the difference. So instead of just trying to use matrix perturbation theory to go from here to here, we are actually slowly moving by looking at these stochastic paths and integrating along these stochastic paths, these differences. So now I'm probably preaching to the choir. I mean, probably people here know this much better than I do, but I think this is a very interesting way to look at perturbations, given the importance of low rank approximations in so many different areas. I think this is something that I personally found very useful. We use this to track and analyze the change in the Frobenius norm on the difference of the low rank approximations. So this is what the result looks like. It is a bit of a mouthful, but it does improve upon the previous works of the authors that I mentioned earlier by essentially a factor which is square root k. So the bounds that they could prove, the earlier works could prove as to how far these two quantities will be in the Frobenius norm were not tight. And in fact, this Dyson Brownian motion view of things allows us to improve those bounds. Am I done with for time? Okay, so I think I'm gonna just skip the proofs. This is some nice. And just conclude. So in conclusion, hopefully this talk gave you some idea of the interplay between designing efficient private algorithms and the area in which all of you are expert in. And in some sense, you know, it's very close in certain dimensions. And the two results that I talked about, one was a contribution from computer science to statistical physics, which is to sample from these HCIZ densities. And the other was using ideas from statistical physics to design these new algorithms. I think illustrate this interplay. There were some assumptions in our work on this Brownian motion. In particular, once you're looking at these stochastic trajectories, it becomes important that these things don't come very close to each other in the analysis. And so for that, there were some assumptions on the gaps of the eigenvalues to start off with. And this is something that we have removed by further using and connections to random matrix theory and other such areas. So I will just stop here and thank you. Sorry for going over time.
Thank you. Questions?
Yes.
If I understand correctly, your M is a Wishart matrix, right?
M is a
Wishart matrix.
No, because if M is a Wishart matrix when the data matrix is distributed according to some distribution. So maybe this point was not completely clear that we are working with worst case matrices. So we are not working with matrices whose data comes from random, data is randomly generated. This could be any matrix.
Yeah. So
Yeah.
M is a form of A transpose A, right?
Yeah, it's a covariance matrix. Yeah.
Yeah. Okay.
Yeah.
So that is what I called Wishart matrix.
Okay.
Yeah. So actually, the Brownian motion analysis of Wishart matrix have been done by Akhilesh Pandey and Santosh Kumar, whose students are here.
Mhm.
So you can, I mean, like, if you are interested. And Dyson Brownian motion model, a lot of work has been done by Akhilesh Pandey and Madan Lal Mehta.
Yeah. There's a lot of work
yeah.
on that. Yeah.
So
Absolutely, yeah. But I think this specific thing of computing the change in utility or change in the Frobenius norm of the low rank approximation to this matrix. So a lot of the work has focused in this space where you have a matrix, you add noise to it, you track its eigenvalues. What I'm saying here is that you actually look at the low rank approximation to this matrix and then see how that evolves. This doesn't have any equations. like Dyson Brownian motion. This is what we are doing. So this in some sense is a much more complicated process because the solution, this is a solution to an optimization problem involving the matrix. So when you're going in this space, you're taking a stochastic trajectory. Yes, the eigenvalues and the eigenvectors you can write as a function of time here in this space. Okay, but what happens here is a completely different story. But of course, the ideas are useful. So, yeah.
I mean, for the first epsilon delta differential privacy algorithm, why not just sample from the Gibbs measure on the manifold? I mean, there exists like methods from like free energy computations in computational statistical physics for that method. Like, I mean, there's like
How do you do that?
you can do a HMC on a manifold.
But what's your guarantee of its convergence?
Well, it exponentially mixes, so you have like probabilistic guarantees and like you use like some
But I mean,
techniques
what we want is a running time bound. So I mean, what does it even? So I mean,
yeah, you can prove contractivity estimates.
Yes, you can prove contractivity estimates, but you still need, first of all, you need to discretize these trajectories because you can't really run continuous time processes.
Yeah.
Right. And then because of the curvature of the manifold, you will start seeing that the step size that you have to take will become larger and larger over time. And so in the end, if you want to control the error, so you have a continuous trajectory and you're approximating it by a discrete trajectory. So the errors will keep growing. So in the end, I mean, I know very well what you're saying. I mean, but these algorithms don't lead to efficient algorithms. They lead to some algorithms.
Okay.
Yeah.
Okay, so if there are no more questions, let's thank
Thank you so much.